So here I've got a space curve. And when we draw these space curves, these vector functions, we know that its position is given by, in this case it's 3D, so r of t is given by an x, a y, and a z, and the x coordinate's a function of time, and the y coordinate's a function of time, and the z coordinate's a function of time. This one is built with trig. The x coordinate is sine 2t, the y coordinate is just cosine t, and the z coordinate is 3 sine of 4t times cos of t. So it gives you this shape. Whatever, I know that its position is given by the r. If I take the derivative of that, r prime, we were talking about that as the tangent vector. But the tangent vector gives me, it's a vector, it gives me two pieces of information. Its direction, which tells me where it's going, and its magnitude, which tells me, well, how fast it's moving. So if I'm thinking of this as position, then its derivative, so the r is position, then its derivative is going to be its velocity. So the tangent vector is its velocity. Velocity is a vector function, so it has direction, where you're going, and how fast you're going, the magnitude. If I just take that magnitude of the tangent vector, then that's speed. So, and what if I just wanted the direction that it's going? Well, that's what the unit tangent vector is for. It has a magnitude of 1. If I take the second derivative, that's the derivative of velocity, that's acceleration. If position is in meters, then velocity would be in meters per second, because I'm taking the derivative with respect to time, and acceleration would be in meters per second squared, because I'm taking the derivative of velocity or the second derivative of position, however I want to think about it. So this video is supposed to be connecting our space curves, our vector functions, with some physics applications. So basically I'm just putting a velocity, speed, and acceleration story on the map that we already know. So here's and I should put vector hat over that. Here's a question. I've got a vector function. I want to know, when is its speed a minimum? Well, okay, let's get the speed function. The speed function is the magnitude of velocity. So the first thing I need then is I need to find the velocity vector. So I'm going to take the derivative. 1, 2t, and 1 minus 10t. Okay, so that wasn't too bad. There's the velocity vector. To get the speed, that's supposed to be the magnitude of the velocity vector. So that's going to be square root of first component squared plus second component squared plus third component squared. Okay, and we could expand that out, we could clean that up, we'll do that in a minute. But here's the speed. Now speed is a function of time. Now what am I wanting to do? I want to find the minimum of that. Now this is a single variable first year, first calculus course question. Here's a function of time, find its minimum. So I know mechanically what I'm going to do. I'm going to take its derivative, so I have speed equals. I'm going to take its derivative, I'm going to set it equal to 0, and I'm going to solve for time. And that's the when is the speed a minimum. Now, if they asked what was the minimum speed, then I would do the same thing, but I would find that time and then plug it in and find what the speed was. Or if the question was, where is the speed a minimum? Then once I find out when the speed is a minimum, I'll know the t. I can plug it into the position to find out where the speed is a minimum. I can plug it into the speed function to find what the smallest value is. It all hinges on me taking the derivative. But I'm going to make my life a little bit easier here. Because if I'm looking at it right now, and I have to differentiate the thing with the big square root sign in it. If speed is a minimum, then speed squared is a minimum. So I'm going to make up a new function, which is speed squared, and I'm just going to minimize that. Let's expand and clean that up a little bit. Just makes our math a little bit simpler. So that's speed squared. So now I'm getting the derivative of that. Oh, it's a t squared, positive t squared. It's a parabola. So I'm looking for the minimum of that. I'm looking for the denominator. I'm looking for the vertex, the bottom of the parabola. So let's take our derivative. I took the derivative. I'm setting it equal to 0. Straight solve for t. So at 5/52 seconds, the speed is at a minimum. Although, as soon as I got my speed function, all of this stuff, taking the derivative and set equal to 0, that's single variable calculus from previous classes, right? The only thing that's connected to this video, velocity, speed, and acceleration, is, oh look, I got the speed function. Here's another physics question. And it's the same, well, it's the same thing as far as I forgot to put a vector hat on it. Now it's a vector. This is the position. What force is required to keep for a mass to keep the particle's position at? So the position is changing. I'm looking for the force function. So I have to know a little bit of, very little bit of physics. We know that F equals ma. Force is mass times acceleration. Force is a vector function. Acceleration is a vector function. I know what the mass is. It's m. I just need the acceleration. So I need to get the second derivative. So here's the position vector. I need the acceleration vector. So the velocity vector, I'll use that for v, take the first derivative. There's the velocity vector. The acceleration vector, I'm going to take the derivative of the velocity. So here's my acceleration vector, r prime prime, 6t. And finally, to get the force vector, I just have to multiply it by the mass. So that's going to be 6mt, 2m, a constant 2m in the y direction, and no force in the z direction. So there's my force. I've answered the question. Let's look a little deeper at this for now, though. Notice the z component is 3t. So for every second that goes by, it just gets 3 meters higher. It moves in a constant velocity. Oh yeah, its derivative is just 3. In the z, the velocity is constant. Constant velocity means no acceleration. Yeah, that's why it's a 0. The t squared, that's like something falling in the y, like a gravity. So it has a velocity that's ever increasing in the y direction. Yeah, because there's an acceleration. It's going faster and faster and faster in the y direction. Now, in the x direction, the velocity is a function of t squared. The acceleration is ever increasing. So a prime, I could take a prime and not get a 0 vector. The a prime is 6, 0, 0. That would be the jerk vector from physics. Anyway, this whole section is just basically summed up with these bullet points. Oh, we're going to do some physics problems with the math that we already know. By the way, I'm thinking of the vector function as giving position, so its derivative means velocity. So the magnitude of that derivative is speed, and the second derivative is acceleration. And I guess I could put another bullet for the r prime 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 is the jerk vector. But that's like too far into the, we're not going to get that deep into physics. That's it.